In this lesson, we'll discuss learning target number 5, determining and describing the density of a gas. Also, determining the molar mass of an unknown gas and determining its molecular formula. Density is another quantitative physical property that we can describe about gas samples. Since all ideal gases have the same molar volume at STP, but they have different molar masses because of different particles, different gas samples will have various densities. Some gas samples will float in air, while others will sink in air. The density of air is 1 gram per liter. Density is calculated by taking the mass of the sample and dividing it by the volume. Let's do some example calculations. In order to calculate the density of hydrogen gas at STP, let's take a fictitious 1 mole sample. The mass of 1 mole of H2 gas would be equal to the molar mass of the formula, which is 2.02 grams per mole. And the volume, because I have a 1 mole sample at STP, would be 22.4 liters. I can round this answer to 3 sigdigs. This is much less than 1 gram per liter. That means that hydrogen gas samples float. Let's calculate the density of a CO2 sample. Its mass would be 44.01 grams, the molar mass of CO2, divided by the same 22.4 liters because I have a 1 mole sample at STP. I can also round this answer to 3 sigdigs. CO2 has a higher density than air. It's almost double. That makes CO2 gas samples float. It's important to know the density of different gases if you're trying to collect them when doing experiments. Because hydrogen gas is less dense than air, I need to keep my container upside down when I collect the hydrogen gas. And I need to put a lid on it so that it doesn't try to escape. For CO2, however, I don't need to do that. Once I've collected the CO2 gas, it's going to stay in my beaker even without a lid because it sinks. Now the density of different gases can cause other health hazards as well. In the copies of the old textbook in the classroom, there's a story about the killing lakes of Cameroon. The story describes how 2 villages were totally killed by volcanic lakes dumping huge amounts of CO2 into the village. All of the inhabitants were suffocated because CO2 is more dense than air and got trapped in the valley. Let's do some density examples. In example 1 here, we're calculating the density of pure chlorine gas, but not at STP. It gives us different temperature and pressure values. We need to use the equations that we know in order to find the mass of the sample and the volume of the sample so that we can then calculate the density. Notice in the question it doesn't give us the amount of gas they want us to use. The density doesn't change if I use 1 mole or 1,000,000 moles. So you get to choose how much gas you want to take. So let's take a 1 mole sample again. The density will be the mass of that sample. Because it's Cl2 gas, I take the molar mass of chlorine and times it by 2. I get 70.90 grams. And now I need to find the volume of that gas sample. Because I know the moles, I chose that, and I have the temperature and the pressure of the gas sample, I can use the ideal gas law and solve for V. I can now sub that into my density equation. Now, I could probably keep 4 sigdigs, but I defined a 1.00 mole sample, so I'll round this to 3. Now that we know the ideal gas law, we can determine the molar masses of unknown gas samples without using a mass spectrometer. If we use percent composition data or a CH analyzer or experiment, we can then determine the molecular formula of an unknown gas. Example 1 shows you the process of determining the molar mass of an unknown gas sample. A scientist finds that 9.72 liters of a gas sample has a mass of 8.75 grams at STP. The experiment is pretty straightforward. You take a gas canister that you know what the volume is, and you measure the mass empty. You put your gas sample in it, and then measure the mass after. The difference in the masses is the mass of your gas. You then attach a pressure gauge and a thermometer, and you can measure the temperature and the pressure. Just by measuring this physical data, we can determine the molar mass of the unknown gas sample. I'm going to start by calculating the amount of moles in the gas sample using the ideal gas law. Let's start with the ideal gas law and sub in the information we're given in the question. My pressure is 101.3 at STP. The volume of the gas cylinder is 9.72 liters. And I'm going to solve for moles. I can then use the mass equals moles times molar mass equation from Unit 3 to determine the molar mass of this gas. The mass of the sample is 8.75 grams, and I know how many moles it contains. So the only thing I'm missing is the molar mass of the gas. I can rearrange that. What I do is I take the mass and divide it by the moles. That'll isolate capital M. Now I can only have 3 sigdigs in my answer. So this unknown gas has a molar mass of 20.2 grams per mole. Example 2 puts the whole process together, starting with percent composition information. We can use this to determine the empirical formula of an unknown gas sample. Remember, we start this process by taking a 100-gram sample and go through our 7 steps for identifying a compound. Step number 1, we find the mass of each piece of the formula. I know it's been a while, so we'll do this example together. Here's my organization chart. Now if I have a 100-gram sample and it's 80.0% carbon, then I'm going to have 80 grams of carbon. And then the rest of the 100 grams will be hydrogen. Step number 2, change each of these values into moles. I do that by dividing by the molar masses of the elements. Step number 3 of the process is to divide by the lowest number. That sets my ratio equal to 1. The H's, when you work that out, ends up being 2.97. Because of our special rounding rules, we don't have to do step number 4, which is, if you remember, multiply your number by 2 to 6, if necessary, to get a whole number. Because my decimal is greater than 0.90, I can just round this to 3, and my empirical formula is going to be equal to C1H3. Now the next step would be to find the molecular multiplier. In order to find that, you take the molar mass of the unknown compound and divide it by the molar mass of the empirical formula. Well, a CH3 weighs 15.04 grams per mole. In Unit 3, you were given the molar mass of the compound using a mass spec. But because this is a gas sample and we know the ideal gas law, we can now calculate the molar mass ourselves, like in example 1. The pressure of the second gas sample is 152 kPa, and I have 2.50 liters of it. That was given to me in the question. I can use the ideal gas law to find out how many moles were in that sample. It also tells me in the question that I've got a 4.60 gram sample. I can use mass equals moles times molar mass in order to figure out the molar mass of this unknown gas. Once I have the molar mass of the gas, I can find my molecular multiplier. So the molecular formula is going to be C1H3, and my atoms need to be times by 2. So the unknown gas is C2H6. Complete the density and molar mass questions listed on your assignment cover sheet.